morning, students. In the today's class we will be studying the topic known as the FIR filter design using windowing techniques. In this class we are able to understand how to design a FIR filter and what are the different types of windows that can be used for the design of the FIR filter. So basically FIR filter is having a finite impulse response and which is characterized by its linear phase. If you see the filter which you have designed in the previous class, that is IR filter, and the frequency response has the infinite number of the impulse response, and that is characterized by its non-linear phase characteristics. Then the question is how to modify the number of impulse responses in the IR filter. The one option is to use the windows, and using windows you can truncate the impulse responses of the ideal filter on both right hand as well as left hand side of the IR filter, and by doing this one you can limit the number of impulse responses in the IR filter, so that you will get only the finite number of the impulses in the frequency response of the FIR filter. So this is the basic idea of using the windows techniques in design of the FIR filter. So the main purpose of using the windows technique is to limit the number of impulse in the frequency response of IR filter, so that you will get the linear phase characteristics in the FIR filter. So that is the basic idea of using the windowing techniques in design of the FIR filter, right? So the design of FIR filter using windows technique is nothing but we have to obtain the filter coefficients in both time domain as well as a frequency domain, right? So before that we have to truncate the frequency response of ideal IR filter in order to have the frequency response of the FIR filter. So how to truncate? So the truncating the impulse response is nothing but multiplying the impulse response of IR filter with the window function. So there are different window functions in digital signal processing. We will study those one by one later. So let me understand here is, if HD of n is the impulse response of the ideal IR filter which is having infinite number of impulse response. Now let us truncate this impulse response HD of n at n is equal to 0, because we are interested in the causal FIR filter, and it is possible to do by multiplying HD of n with W of n in order to have H of n. So here HD of n is the impulse response of IR filter, W of n is window function, and this window function is defined if you consider a rectangular window, and this rectangular window is defined by W of n is equal to 1 for 0 to n minus 1. So 0 to n minus 1 means how many number of impulse you will get, samples you will get, the finite number, that is n number of samples we have to choose for the rectangular window. And outside this range from 0 to n minus 1 we don't have any sample values, so W of n is equal to 0. And such window function, rectangular window function, if you multiply with HD of n, that is nothing but impulse response of IR filter, the resultant function, the impulse function you will get is the FIR filter impulse response, that is H of n. And if you take the Fourier transform, discrete time Fourier transform over both sides, so what you will get? H of W is equal to HD of W into W of omega, because So here it is in time domain, it is simple multiplication, and if you perform the discrete time Fourier transform in the frequency domain, the simple multiplication turns out into what? The convolution, right? So of course, like HD of W is equal to H of W, this means that this W of omega must be equal to delta of omega, because in time domain it is nothing but it is delta of n is equal to 1, right? So that is what given here, W of n is equal to 1 for all n in time domain, and after performing its discrete time Fourier transform, this W of omega should be equal to delta of omega, right? And if you take the calculate the frequency response of this window function W of n, basically it is 1 for 0 to n minus 1, right? So here it is summation 0 to n minus 1, W of n is equal to 1. Fourier transform means you have to multiply by a complex exponential function, that is e raised to minus j omega n, and using the property of summation when it is 0 to n minus 1, so you will get 1 minus e raised to j omega capital N divided by 1 minus e raised to minus j omega. From both numerator and denominator, if you take e raised to j minus j omega n minus 1 by 2, right? So what you will get? You will get sine omega n by 2 divided by sine omega by 2, right? And this sine n theta divided by sine theta. So this is nothing but what? The sinc function used to reconstruct any sampled signal, right? So here it has both phase as well as magnitude, e raised to minus j, so that is the phase value, that is minus omega n minus 1 by 2, and this is the magnitude, sine omega n by 2 divided by sine omega by 2, right? And for different values of omega, if you plot its magnitude, so you will get like this, right? So there is a main lobe, and these are nothing but what? Side lobes, and these side lobes are also known as the ripples in the stop band. So basically this is minus 2 pi by n to 2 pi by n, so this is a pass band, right? So this is the width of main lobe, and these are the side lobes, and these side lobes are also known as the ripples in the stop band. So because of this this nature, right, so the FIR filter exhibits the linear phase characteristics. And now here we'll discuss the different types of the windows. Basically we have the 4 types of, even though here we have 6 types of windows, in our syllabus we have the 4 types: the rectangular window, Hamming window, Bartlett, and the Kaiser window. So we'll discuss one by one here. The rectangular window, which is the most simple to use and widely used the window function in designing the FIR filter, because of its the simple definition as well as its impulse response, right? And if you take the frequency response of this one, so frequency response will have both a main lobe as well as side lobe, that is the ripples. The width of the main lobe is given by 4 pi divided by n, where n is the number of the impulse samples in the impulse response, which is given by 4 pi divided by n. And the window function is defined by, in the time domain, the rectangular window function is defined by WR of n is equal to 1 by 0, n is equal to 0 to up to m minus 1, and otherwise outside this range it is 0. And the magnitude response of rectangular window function is sine omega m by 2 and sine omega by 2, right? So this is the magnitude response of rectangular window. So if the question is asked like with the equations or expressions, explain different types of windows, you have to write the definition, then what is the mathematical equation for rectangular window, and what is expression in frequency domain. Along with these plots you have to draw. And next one is Hamming window. The Hanning window is defined by mathematical equation W of n is equal to 1 by 2 1 minus cos 2 pi n divided by m minus 1, and in frequency domain it is given by this equation. And the plot of Hanning window in time domain as well as frequency domain looks like this, and here the width is 8 pi divided by n. So these equations are very useful when you are solving the examples on the filter design using various window techniques, right? And then comes is Hamming window. The window function is mathematically defined as 0.54 minus 0.46 cos of 2 pi n divided by m minus 1. So this is the most widely used the window function in signal processing application. Then this is in frequency domain. This is Hamming window in time domain, that is the impulse response. So this is a frequency domain. And next comes is Blackman window. Again this is the time domain equation, frequency domain equation, and these are the plots in time domain as well as frequency domain respectively. And last one is Kaiser window, and this is the equation. So these are the two plots, and here this table gives you a brief idea about different types of windows as well as their window functions. So this is rectangular window and their window function is given by this equation. Triangular or Bartlett, Hamming window, Hanning window, Blackman window, right? And these are what is the transition width of main lobe, that is from passband to stop band. So what is the width available between the main lobe and a side lobe, and there is transition of course. So this is the minimum stop band attenuation for each window and peak value of the side lobe. So what are the design steps for linear phase FIR filter? So the design steps includes, based on the desired frequency response specification HD of e raised to j omega, determine the corresponding unit sample response, right? So they will give the frequency response of IR filter in the first step. In the problem statement they will give the frequency response of the ideal IR filter, that is HD of e raised to j omega. So you have to perform the inverse Fourier transform so that you will get HD of n. So this HD of n is the inverse Fourier transform of HD of e raised to j omega, right? So that is performed using this equation, 1 by 2 pi from minus pi to plus pi, HD of e raised to j omega e raised to j omega n into dWn, right? And they will also ask you to use the particular window function. Either you may get the rectangular window to use, or Hanning window to use, or Hamming window to use, and also they will specify the length of the window, the capital N they will give, right? So if they mention the type of window you have to use, so if the rectangular window you are asked to use, then you have to multiply WR of n. So that WR of n is nothing but the rectangular window function, that you have to multiply it with the HD of n. What is this HD of n? It is the IR filter impulse function. So once you multiply HD of n with W of n, it is as good as truncating the impulse response of IR filter to get the impulse response of FIR filter. So you will get H of n. Then you substitute n is equal to 0 to up to n minus 1. So that n is nothing but the total length of the window function, that is the duration of window. So you will get the finite number of samples in the FIR filter. Understood? So then you take again Fourier transform, right? Then you will get H of e raised to j omega by substituting W value you will get again the sample values in the frequency response. So this is how we design the linear phase FIR filter. So in the next video we will discuss how to design the FIR filter using different window function. So that is very important for examination point of view. Thank you.